Thermodynamics in Biosystem Module 3 Energy Segment 1 Forms of Energy with me Yusuf from School of Life Sciences and Technology Institute Teknologi Bandung. In this module we will discuss about forms of energy, energy transfer, mechanical forms of work, first law of thermodynamics, energy conversion efficiencies, and last but not least energy and environment. Energy can exist in numerous forms such as thermal, mechanical, kinetic, potential, electric, magnetic, chemical, and nuclear, and their sum constitutes the total energy of a system, which can be expressed by equation 3.1. Thermodynamics provide no information about the absolute value of the total energy. It deals only with the change of the total energy, which is what matters in engineering problems. Thus, the total energy of a system can be assigned a value of 0 at some convenient reference point and independent of the reference point selected. In thermodynamic analysis, it is often helpful to consider the various forms of energy that make up the total energy of a system in two groups, macroscopic and microscopic. The macroscopic forms of energy are those a system possesses as a whole with respect to some outside reference frame such as kinetic and potential energies. The microscopic forms of energy are those related to the molecular structure of a system and the degree of the molecular activity, and they are independent of outside reference frames. The sum of all the microscopic forms of energy is called the internal energy of a system and is denoted by symbol U. The macroscopic energy of a system is related to motion and the influence of some external effects such as gravity, magnetism, electricity, and surface tension. The energy that a system possesses as a result of its motion relative to some reference frame is called the kinetic energy. When all parts of a system move with the same velocity, the kinetic energy can be expressed by equation 3.2. The energy that a system possesses as a result of its elevation in a gravitational field is called potential energy and can be expressed by equation 3.3. The magnetic, electric, and surface tension effects are significant in some specialized cases only and are usually ignored. In the absence of such effects, the total energy of a system consists of the kinetic, potential, and internal energies, which can be expressed by equation 3.4. Most closed systems remain stationary during a process and thus experience no change in their kinetic and potential energies. Closed systems whose velocity and elevation of the center of gravity remain constant during a process are often referred to as stationary systems. The change in the total energy of a stationary system is identical to the change in its internal energy. In this text, a closed system is assumed to be stationary unless stated otherwise. Control volumes as shown in the figure typically involve fluid flow for long periods of time, and it is convenient to express the energy flow associated with the fluid stream in the rate form. This is done by incorporating the mass flow rate m, which is the amount of mass flowing through a cross-section per unit time. It is related to the volume flow rate v, which is the volume of a fluid flowing through a cross-section per unit time as shown in equation 3.5. The dot of a symbol is used to indicate time rate throughout this module. Energy flow rate associated with the fluid flowing at the rate of which can be expressed by equation 3.6. Internal energy is the sum of all the microscopic forms of energy of a system. To have a better understanding of internal energy, let us examine a system at the molecular level. The molecules of a gas move through spaces with some velocity, and thus they possess some kinetic energy. This is known as the translational energy. The atoms of polyatomic molecules rotate about an axis, and the energy associated with this rotation is the rotational kinetic energy. The atoms of a polyatomic molecule may also vibrate about their common center of mass, and the energy associated with this back and forth motion is the vibrational kinetic energy. Electrons at outer orbits have larger kinetic energies. Electrons also spin about their axis, and the energy associated with this motion is their spin energy. Other particles in the nucleus of an atom also possess spin energy. The portion of the internal energy of a system associated with the kinetic energies of the molecules is called the sensible energy. The average velocity and the degree of activity of the molecules are proportional to the temperature of the gas. Therefore, at higher temperatures, the molecule possesses higher kinetic energies, and as a result, the system has a higher internal energy. The internal energy is also associated with various binding forces between the molecules of a substance, between the atoms within a molecule, and between the particles within an atom and its nucleus. If sufficient energy is added to the molecules of a solid or liquid, the molecules overcome these molecular forces and break away, turning the substance into a gas. This is a phase change process. The internal energy associated with this phase of a system is called the latent energy. The phase change process can occur without a change in the chemical composition of a system. The internal energy associated with the atomic bonds in a molecule is called chemical energy. During a chemical reaction, such as a combustion process, some chemical bonds are destroyed while others are formed. As a result, the internal energy changes. The nuclear forces are much larger than the forces that bind the electrons to the nucleus. The tremendous amount of energy associated with the strong bonds with the nucleus of the atom itself is called as nuclear energy. Static forms of energy refer to the energy that can be contained or stored in a system, whereas dynamic forms of energy or energy interaction is the form of energy that is not stored in a system. Dynamic forms of energy are recognized at the system boundary as they cross it, and they represent the energy gained or lost by a system during a process. The only two forms of energy interactions associated with a closed system are heat transfer and work. An energy interaction is heat transfer if its driving force is a temperature difference, otherwise it is work. Mechanical energy can be defined as the form of energy that can be converted to mechanical work completely and directly by an ideal mechanical device such as an ideal turbine. Kinetic and potential energies are the familiar forms of mechanical energy. Thermal energy is not mechanical energy since it cannot be converted to work directly and completely. A pump transfers mechanical energy to a fluid by raising its pressure, and a turbine extracts mechanical energy from a fluid by dropping its pressure. Therefore, the pressure of a flowing fluid is also associated with the mechanical energy. Note that the pressure itself is not a form of energy, but a pressure force acting on a fluid through a work distance produces work, called flow work, in the amount of P per rho per unit mass. Flow work is expressed in terms of fluid properties, and it is convenient to view it as part of energy of a flowing fluid and call it as flow energy. Therefore, the mechanical energy of a unit can be expressed on a unit mass basis as shown in equation 3.7 and in the rate form as shown in equation 3.8. In the next segment, we will discuss about energy transfer. Until then, I am Yusuf from Institut Teknologi Bandung.